Okay. Good afternoon, dear participants. The topic of today's lecture is the application of remote sensing and GIS in soil resource assessment. Yeah, in this lecture, I will cover concept of soil resource mapping, land evaluation, how we can use this soil map for assessing its potential that we know as the land evaluation. After using the lands get degraded. So how these degraded lands can be mapped using remote sensing data. Today, hyperspectral remote sensing data is also available, which can be mapped for a quantitative estimation of soil properties. Then we also cover the digital soil mapping, soil carbon stock assessment, which is required for the climate change studies or global warming. So soil carbon stock is one of the important issue. And we will also see that with the soil quality assessment, how we can assess using remote sensing in GIS. If we see that is a soil, then soil definitions we define. It is not just the upper surface layer of earth surface, but for us, soil be considered as a natural body which is in three-dimensional, where depth, where length, width, and depth, three things are there. As you know, that is the soils, we study the padon, or we call it a soil profile. And soil profile, it is composed of various layers. That is top layer, surface layer. We call in the forest area, you will get the dark color layer, O horizon. But if it is agricultural land, you will get only A layer, agriculture layer, then B layer, and C, which is the parent material layer over which the soils has been formed. If we see that in this property, soil properties, which you are seeing in this, it is governed by the climate, land use, land cover, and the parent material or rock material or over which this soils has been developed, and the properties is also affected by the topography over a period of time. So this, so we can say that is a soil, for a soil scientist point of view, it is a three-dimensional body, and we study the soil up to the C layer, or which is the layer having the parent material. When we study with the remote sensing data, as you are aware that we study the reflectance characteristics, and similarly, if soil is fallow or area is fallow and soil is open, then we can see that reflectance characteristics of the soil. If soil is darker because of the organic matter, you see that is the darker is because of the iron content, or sometimes it is dark because of high organic matter content, as you are seeing the sea soil. If organic matter is high, then soils are darker, it gives the low reflectance. But if soils having low organic matter, then it is light colored and it gives the highest reflectance. So I can say that is different soils having different compositions give different or variations in soil reflectance characteristics, which helps us to analyze with the remote sensing data for the soil characteristics. When we consider the soil composition, then you can say the 45% soil is composed of mineral matter, air, water, and organic matter. So this is the general composition, and 45% mineral matter we can say that is the composed of sand, silt, and clay material. When we talk about the remote sensing data, so we found that remote sensing data is very useful for soil studies, because remote sensing data provide you a synoptic coverage of the landscape. Large area you can see at one time. You can see the land use, topography, landforms in a one glance, And also remote sensing data provide you the temporal data, means you can get of various month, or you can get before rainy season and after rainy season, then changes can be analyzed. And another advantage of remote sensing data, you are able to derive the digital elevation model DEM, and you can see the 3D surface of your landscape. So 3D surface gives you impression about the topography. So it is very useful for information useful for soil mapping. So then questions comes when we should select satellite data of which time. So generally for soil mapping, we take the satellite data when the crop is harvested. So land should be fallow. But in the forest area where you are having the permanent vegetation cover, so in that case, you cannot avoid that one. So we can also map, although in the forest area, but the technique is different. And we generally use the standard false color composite, FCC, for the interpretation of satellite data. And mapping of satellite data in general, operational methods, we use visual interpretation techniques of soil resource mapping. So if we want to map the soil, then it is very important us to understand that how the soil is formed. Where we want to map, the formation of the soil has to be understood. That is, you have to see that is which factors was responsible for formation of the soils. And if we see that is which are the factors have been listed for the soil forming factors, you know that is the soil is the function of, or it depends on the climate, organism, parent material, relief, and time. So these are 5 factors are there, and in these 5 factors, that is the climate and organism is considered as a active factors, and parent material, relief, and time is considered as the passive factor. So passive factor, active factor means it provides the energy to the system or soil system, and passive factors, it provides the condition to development of the soil. So these 5 factors we need to interpret it with the help of remote sensing data. If we interpret these 5 factors with the remote sensing data, then it can assist us, or it can help us in preparing soil map. If we see that is the one image I am showing of the flat alluvial plain, where that is the flat land is there, and you see the different different reflectance characteristics, but sometimes similar reflectance characteristics doesn't mean that is the similar soil. Reflectance may be same, but soil is different. Why? Because soil is different because what is the reflectance you are getting because of land use land cover, and land use land cover is not the primary factor which is governing the variability of the soil. The first factor which governs the variability of the soil is the type of parent material. So if you see the parent material is different, so parent material means mapping of geology or geomorphology. So first task in the soil resource mapping is to mapping geomorphology. Now you see another satellite image. This is shown of the Dehradun area, and this is the hill, Shivalik Hills, and you see one hill having 2 aspects. Topographically, this is the south aspect and this is the north aspect. And you see in the north aspect, it is a dense, bright reddish color that is showing that is the dense forest cover. But in this side, the forest is not so dense. Also, you are seeing that is the landscape is highly dissected in this side, in the south side, but in north side, it is sorry, dissection is not so, you are not seeing that one. It means here the soil development is very good and here soil development is poor. So south aspect of the hill soils are poorly developed, whereas the north aspects are well developed soils. But here what I want to show you, here and here you see both the places, the tonal variation both are dark, both are dense forest, and having the showing as a dark red color. Both the places are appearing similar reflectance characteristics, but soil is not same at both the places, because this is the plain land, means gentle slope. It is not the hill, but this is the this color is appearing on the hills. So because of it is hills and it is plain, so geomorphology is different. That's why soil is different. Even the showing the same spectral characteristics. So what we do for soil resource mapping, we take the standard FCC false color composite. We derive from this satellite image. We generate the parent material map, which is you call geology map. We can generate the topography map. Although for the topography we can use a digital elevation model also, but satellite data, high resolution satellite data also gives the 3D perception, and you can use to interpret the remote sensing data for topography as well. And third informations we derive from the land use, land cover, which is the organism. So in general, if in any area, which is any region or in a district, if you have to prepare the soil map, then you have to interpret all these three informations, and you can generate the integrated map where all these three informations are there, and we call it is soil landscape map. Okay, so in this climate and time, two factors are remaining of soil forming factors, which we considered as a constant, which is not changing significantly. Now I show you one example. You see this satellite data. If I see as I want first to prepare the geomorphology map or geology map, you can see very well from the remote sensing data. I can interpret hills, and this is the foothills. I am calling it as Piedmont Plain, and this is the alluvial plain developed by or deposited by your river, Ganga River. So this is the alluvial plain. So all these three major division of soil type. So all these three places, soil types will be different. Even here, if you see, here you are seeing that is here the material is deposited by the river in vicinity, but here it is floodplain. So soils here and here is also different. So first task is to map geomorphology. Then you can generate the drainage map of your area, or you have digital elevation model, and based on that you see from here the slope is elevation is high, here elevation is mid, and here the lower elevation. So 3 zones are there. So you can divide your area into three slope classes, broadly in 3 slope classes. So you have also taken care of topography. And third factors, we need to take the land use, land cover. You see, this is the crop land and this is the forest land. So crop and forest lands we divide further, because soils, even the geomorphology is same, topography is same. If land use is changing, then it means soil is also changing. So we can say we have to integrate the third factors, land use, land cover. You can then be prepared like this map. First we prepare the geomorphology map, then it further divide based on the topography or slope map, and then further divide based on the land use, land cover, and we get this by integration of one combined map, which we call it is physiographic map, or we call it is soil landscape map. Now you can take we can consider that the entire area which is having same geomorphology, land use and topography, so in the entire area soil will be same. But what kind of soil is there? You have to go to the field and see the soil profile, characterize soil profile. So 1 or 2 soil profiles we can study in this one, and we can tell that is what kind of soil is there. So you see, then what we do, we select one sample strip or one road, and we go to take the soil profile study at various physiographic units. So you study the soil profile, and you can prepare the soil information. So how we do the soil profile? You see in the field we go and dig the soil profiles, and you can see top layer is, you see like this one, means fine textured soils, but C layer, which you are seeing the stones here in this one. So soil profiles from the surface, reflectance characteristic is not, will not tell about this the subsurface characteristics. That's why we need to integrate the soil forming factors to get the physiographic unit, and each physiographic unit we have to go to collect the soil profile and collect the soil samples. Then only we can characterize the soil type in the particular physiographic unit. So you can see that is the how the, here you see the rock, and over weathering of this rock, this soil is formed, and here dense forest is there. So even the forest area, we can map the soils, but you have to dig up the soil profiles and study that one. So overall methodology is like that one. You do the remote sensing data visual interpretation and study the soil profiles, collect the soil samples and analyze the soils, and then you can make the soil map. So you can prepare the soil map in this one. So then physiographic map is the soil map, and when you combine or integrate the information of your soil profile, then it becomes the soil map. And soil samples has to be analyzed in the laboratory for its basic properties. So soil, then only you can prepare the soil map. Directly from the remote sensing data, we can only ascertain where to take the soil samples and what will be the mapping area, mapping unit. But after preparing the soil landscape unit or preparing the physiographic map, you have to study the soil profile in the field and collect the soil samples, analyze the soils, then only you will able to prepare the soil map. So soil map we can prepare with the remote sensing data of different scale. Soil maps in standard scales are there. 1:20,000 or larger. Then we call it is detailed soil map. If it is 1:50,000 scale, then we call it is semi-detailed map. And 1:250,000, we call it a reconnaissance map. And you know, you can generate the FCC at this particular scale, and you are having various sensor data, high resolution satellite data. For example, list 4 satellite data, Cartosat 1 and 2 data that can be used for the detailed soil resource mapping, which will be useful for block or village level. But semi-detailed scale, 50,000 scales, you can generate with the list 3 data or Landsat TM or Sentinel-2 data. This scale is useful for district level planning. And 250,000 scales, which we can generate the 50 meter or above spatial resolution sensors, FCC, and it is useful for state and regional planning, this soil map. If you see in India where we get the soil map, then I will like to inform you that in India the ICR having one organization, National Bureau of Soil Survey and Land Use Planning, but they provide the soil map at 1:250,000 scales, which is useful for your state level planning or regional planning. They have generated 1:250,000 scale. But district level plannings, you need 1:50,000 scales, which has been not generated for the entire country. Only 36% of our country's geographical area has been generated, has been prepared, and some of the states have generated at 50,000 scale. And soil information at larger scale for the village and block level planning, that map is very scanty and very few limited area it is available. That's why we need to understand how we can prepare soil map by ourselves. We cannot prepare the standard soil map without a soil survey team, but we can prepare a physiographic soil map to decide where to take the soil sample, so primary basic characteristics of the soils can be generated. So this is the interpretation of that one. the physiographic soil map has been generated for that area. You see the various soil map units are there. In each soil map units, we have studied the soils. And then we have prepared, that is your mapping units. And in these mapping units, what is the soil characteristics? Soils are well drained, or what is the depth of the soils, what is the pH of the soils, and texture of the soils can be characterized. So each physiographic unit, we by laboratory analysis and in the visual and in the field studies, some of the characteristics can be mapped and we prepare the soil map. Then this soil map we can use for assessing the potential of the land, and potential of the land can be assessed using land evaluation methods. And one of the most important land evaluation method is land capability classification. Land capability classification, it is in general, it is used to assess the general potential of the land. The land is suitable for cultivation or it is not suitable for cultivation. So we classify into 8 capability class 1 to class 4. That is, if it is come into this class, then we call it is suitable for cultivation. 1 is the highest suitable and 4th is the marginal suitable for cultivation. Then 5th to 8th is the least suitable for any use other than wildlife. Vegetation also cannot grow, and 5th is best suitable for the vegetation purpose. So we classify, we use soil map for preparing land capability classification. Then how we can do this one? For that one, there is a criteria table, because in land capability class 1, 2, 3, 4, the texture, depth, slope, erosion class, this information has been given. If your land is fitting into any class, suppose it is, if it is having this texture, this depth, this slope, then you can say that will belong to the capability class 1. But if it is having slope is more, depth is less, texture is coarse, then we call it is land capability class 8, which is marginal suitable for agricultural land use. So we can assess that is which land is suitable for agriculture and how much suitable for agriculture can be analyzed. Even the soil map, you can then we can prepare the land capability map. So you need soil map and then land capability map. We can generate land capability class 1, 2, 3. You can see like this one. Then again, this soil map can be used to analyze the crop suitability map. Means this which soil is suitable for which crop and what level of suitability is there. Because for the crop suitability analysis, you need a soil map, you need a digital elevation model for analyzing the slope, you need the climatic conditions, rainfall, temperature, or other weather climatic parameters. Using this one informations, you match those criteria, which is crop suitability criteria is given in the literature, and based on that matching, and you can find out the land is suitable for which particular crop. And for that one, the methodology internationally used is FAO framework of land evaluation. So this part that was I have discussed, that is how you can prepare soil map using remote sensing data. How preparing soil map, you need to characterize soils in the field by profile study, and then you can assess the soil map for its suitability for general capability using land capability classification, and also for the crop suitability analysis. Now another aspect of the remote sensing data is also used for the mapping of degraded lands. And in India, you know, the total degraded lands in our country is 120.4 million hectares. You know, that is the India having 324 million hectare total land area, and out of 1/3 is facing the problem of land degradation. And the land degradation, if you see, the wind and water erosion is the contributing 79% of total degraded lands. So you can say 79% wind and water erosion. Acidic soils, which is mainly in the hilly area, 15%. Saline and alkali soils, which is the you will find in the area of irrigated land, and it is around 4.8% area. Waterlogged 1% area. So like this one, this is the total erosion condition, land degradation condition in our country. So major degradations is 80%. Now we will see how these degraded lands can be mapped using remote sensing data. So if we want to map the soil erosion is defined, that is the removal of the topsoil. When suppose here you see because of rains, heavy rains, topsoil is removed, and then you see the stones and others in the hilly area, that soil is left. So if thin layer is removed, then slight erosion. If that is thin and sheet erosion, that is a thin layer of soil layer is removed, then sheet erosion. And sometimes rills are formed in that one. That severe erosion and gully erosion is very, when gully forms, then gully erosion. And when there is, you find network of gullies, then it is called very, very severe erosion. So can we map this erosion class using remote sensing data? Yes. Today we are having a satellite data of various spatial resolution, and we can see all these things. So here you can see here one satellite data I am showing you here. That is the here you see the lot of dissection, dissected land. So it is showing the gullies, network of gullies. When you are having the network of gullies, then it is very severe erosion. And here then it will be the network of gullies is less than this one. It is moderate erosion or severe erosion. And here you see the topsoil is removed, and because of that topsoil, when it is removed, then organic matter, clay material is washed out, and because of that the sand is enriched, sand content becomes high and low organic matter. That's why it gives high reflectance. So moderate erosion is appearing as a high reflectance, so appearing as a whitish in tone. But here you see that is a darker tone, or agriculture you are saying this one because of red stone. So we can say the slight erosion. So slight erosion, moderate erosion, severe erosion, and very, very severe erosion. So these erosion classes we can map directly from the remote sensing data. And even you see this hills is under the dense forest cover, moderately dense forest cover, because here is the dense forest cover, and under the forest cover so much of erosion is taking place. But erosion is the surface feature, and it can be directly interpreted from the remote sensing data. Also for soil erosion assessment, we use various erosion models which are available. Some are empirical models, semi-empirical models, and the empirical models most widely used is Russell revised universal soil loss equation. And this model is defined as a soil loss is the function of R, rainfall, K, soil erodibility, L, length of the slope, S, steepness of the slope, and P is the management practices. So from remote sensing data, we can prepare land use, land cover, we can prepare the soil map, and we take the weather data, integrate all these informations, you can generate the soil erosion risk map through models also. So directly also we can interpret it, and we can also go through modeling, and we can generate the soil erosion risk map. Another soils which I told you the land degradation mainly facing our country is salt affected soils. Salt affected soils, you can say the saline soils where salts are there, and another is alkaline soils. Alkaline soils having high sodium content, but saline soils having neutral salts. So here is the neutral salts, and alkaline soils is the sodium salts, which is alkali in nature, or pH of the soil is high, and sometimes we find mix of the saline and alkaline soils, saline and alkali properties. So how we can see that is the if you see the normal soils, if you see the saline soils, electrical conductivity, salt concentration is more, and sodium percentage is less. ESP means exchangeable sodium percentage, and pH is less than 8.5. Alkaline soils having pH more than 8.5, and salt concentration is medium, and saline alkali soils salt concentration is high and pH is less than 8.5, pH is less. So these soils we can characterize using remote sensing data. You see, I have showing the field picture of salt affected soils. This is in the alluvial plains near to in Uttar Pradesh. You see in the summer season, in the month of May, June, because of high evapotranspiration, because of high temperature, evapotranspiration is increased, and because of that, salts which are available in the soil, within the soil subsurface, they, due to high evapotranspiration, they reach to the surface, and you see on the surface salts get accumulated. When these salts get accumulated, then this will give the high reflectance in the visible wavelength region, and that appears in false color composite as a white tone. So these are all salt affected soils. So we can easily map salt affected soils if we take satellite data of May and June month. And here you are seeing that is the salt affected soils in generally. There you will also find the waterlogged area, waterlogged soils. You see on the surface water get collected, and some area here the soil moisture is high, and when soil moisture is high, it will give bluish tone on your satellite data, false color composite. But when water is stagnated, then it is giving dark bluish tone, appearing as a black, but it is dark bluish tone. So we can easily map because it is the surface, it is governing or it is affecting surface reflectance, because of these soils developed on the surface. So what happens? That is also alluvial plains. Now you can see this is the salt affected soils and waterlogged area. The reflectance characteristics, if you find, then you see the salt affected soils give high salt concentration, will give high reflectance, whereas the normal soil, you see, normal soils is not giving high reflectance, it is giving low reflectance. So as the salt concentration go on increasing, that is your reflectance will go on increasing. This is another pictures of Rajasthan area, false color composite, Indira Gandhi command area. Command area means irrigation area, and you see earlier the entire area was under dune and sandy plains, but you see that is over the period of time it is highly well agricultural land. But you see this is the canal, and along the canal some depressional land, water has been stagnated, so waterlogged area. These are the waterlogged area, and you are getting the bright white tone. This is the salt affected soils, and this white stone, creamy stone is there, which is the sand dunes. So it is not salt affected soils, it is sand dunes, higher topography. But this white tones you are getting, that is the salt affected soils. So the purpose of showing this slide is that in the irrigation command area, we get development of salinity and waterlogging, and those things can be mapped using remote sensing data. Even we can map the temporal growth, that is in 5 years, 10 years, how much area has been increased in the waterlogging and salt affected soils. So I will show you one study. You see in the Haryana, where the entire area is irrigated lands. Most of the area is irrigated lands, and because of canal irrigation. And in that area, when we stayed in Rohtak district of Haryana in 2000, so we get that this is the waterlogged area in that part, and this is the salt affected soils. So we mapped using May month satellite data, and you seeing that is by supervised classification. You see this is the your yellow color is showing the salt affected soils. This is the salt affected soils, and here this is salt affected soils. So what happened when I was analyzing of 1990, then salt affected soils, yellow color salt affected soils you are seeing here, but here there is no salt affected soils. But after 10 years, we also getting salt affected soils in this side. So in 10 years, this much of area also felt that salt affected, and here what salt affected intensity was poor, not much, but its intensity has increased. So in 10 years, the salt affected soils has increased too much, and that's, you can say, remote sensing data can help you to monitor your land degradation or to monitor your health of soil resources. Now, another study is that you know that the hyperspectral remote sensing data is becoming very popular nowadays, and that is although the Indian remote sensing satellite data, we don't have so much of a spatial resolution, but in coming years, hyperspectral remote sensing data will be available. The advantage of hyperspectral remote sensing data is that it provides you opportunity to quantify the soil properties. Means multispectrals, you are analyzing the qualitatives, it is slight, moderate, severe. But in hyperspectral remote sensing, you can get the quantitative, how much pH is there or how much salt concentration is there, because you are having more than 200, more than 100 spectral bands. So you can better analyze your spectral indices to characterize those salt affected soils. So in the same area of salt affected soils, we use the your hyperspectral satellite data, Hyperion, which is launched by USA. Presently, this satellite is not working, but we have taken the data of that one at that time, and they were having 242 spectral bands, and we analyzed this satellite data to quantify the salt concentration, and we generated this much of spectral indices: NDVI, causery, that is NDSI, normalized difference salinity index, brightness index, color index, salinity index, with the sensitive spectral bands. We analyzed the sensitive spectral bands and generated these spectral indices, and then we prepared the images like this one from that satellite data. This is brightness, salinity, colorness index, and then we map the salt concentration, EC distribution. So you see that the salt concentration was mapped by the in that area, and this is the area pockets having high salt concentration, and green is the medium and yellow is the slight salt concentration. So we can quantify by developing the equations using spectral indices. In future, we are going to have number of hyperspectral remote sensing satellites, although that India is planning a HISIS 2 in 2024, where we will have 30-meter resolution and 55 spectral bands. Besides India, other Germany and Japan, USA also, they are going to launch, and they have already launched those satellites. Japan has launched, and we are from satellites we are having availability of hyperspectral remote sensing data. Another things comes, that is the digital soil mapping. Today we want to prepare the conventional soil mapping. I told you, in the beginning I have explained, but there is a scope is going for the digital soil mapping. So digital soil mapping is slightly different from the conventional soil mapping. Here we are going to map the different soil properties directly. So what we do, we study the quantitative relationship between environmental data and soil properties. So we study this relationship, and then we call it is we prepare the soil properties map, not the soil map, soil properties map. And because here we are studying only the surface properties of the soils, we are not interpreting the subsurface, because for subsurface and up to the 2-meter depth or up to the pant material characterizing the soils, you have to study the soil profile or soil pattern. But digital surface properties can be mapped using digital soil mapping technique. And here again the soil forming factors are same, only some factors has been extended, that is we are getting from GPS the geographic location, and that is the extra, otherwise other factors are remain same as we have studied earlier. So how we do that one in this digital soil mapping? Digital elevation model is very important. It provides a very information, very large, better information for and helping us in quantitative analysis of soil properties. This is the digital elevation models. You can generate the slope map. You can generate the secondary attribute information, different indices. We call it is a topographic indices. One is given terrain wetness index, like that one. And what we do, we take the regular interval, the soil samples from the surface soils. You see the we have taken the in a very not randomly, but in a grid, and transect samplings we have done. And for the surface, you have analyzed the total carbon content, nitrogen, phosphorus in the nutrients of the soils in the surface samples. And then we use the geostatistical techniques, geostatistical analysis, and prepare the spatial distribution of organic carbon, nitrogen, and phosphorus map. So this is the you can say the geostatistical analysis is done to prepare the spatial distribution of organic carbon. So here you see the organic carbon content. Darker color is showing the high organic matter content, and this is lighter color showing the low organic matter content. So you can generate the spatial distribution of nutrient in your area. So that is the example of digital soil mapping. We can also one example you can get the generate the digital soil health map also, or soil health assessment. So you can take the soil samples at the regular interval, means grid interval. You see the grid interval 250 meter by 250 meter, one samples was collected in the entire area. Surface samples we have collected and lies in the field, and then we use the geostatistic techniques, IDW interpolation, and that is this interpolations you can say this is the organic carbon map distribution. So high organic carbon, and this is the low organic carbon, phosphorus, nitrogen, and potassium. So all the nutrients have been mapped together. And we can generate the soil quality map. So how we can generate the soil quality? As you know, the soil quality, highest soil quality means it functions good, it provides good productivity, it is good for the environmental quality, it promotes the plant health and animal health. So here you see from the laboratory analysis, we prepare, and by geostatistical methods, we have generated this nutrient distribution map. Then we have given scores and weight, and using this formula, soil quality index, we generated the soil quality map of that area by integrating all these information. So soil quality, it is showing the highest soil quality, and this area is showing the lowest soil quality in terms of the nutrients. So you can say this area is deficient in soil nutrients, so low quality. So for getting good crop yield, you have to do focus more for the nutrient fertilizer applications in this area. Although this area is inherently rich in nutrients, not required much applications of the fertilizer, but this is the medium category. So this type of analysis you can do using remote sensing data, field work, and applying GIS technique. In the last 2-3 slides, I will tell you that is we can use remote sensing data, or we can, in soil studies we also go to study soil carbon stock, means how much carbon present in our soil. As you are aware that soil carbon is very important for global warming, and we need to assess that is the carbon stock in our soils. As you know, the Earth's surface soil is the second highest that is sink of the soil, sink of the carbon. Highest is the ocean, second highest is the soil, and then it comes to the atmosphere, and then it is vegetation. If I say vegetation cover of the earth's surface contains 560 petagram of carbon, whereas the soil contains 1 meter depth of the soils contain around 2000 petagram of carbon. So it is 4 times of your vegetation carbon is stored in your soil. So if this carbon is released to the atmosphere, then you can understand how much temperature of the global temperature will increase. That's why soil carbon assessment or stock assessment becomes very important in coming years when you are studying the climate change and global warming. So soil carbon stocks you can assess if you take the surface soil samples. Suppose you want to study of 25 centimeter depth of the soils, take the surface samples and study and go to the library and find out the soil carbon content, how much carbon is there. Then you study the depth and soil bulk density and how much coarse fragment, if it is stony soils are there. So what stones are there, that also you can include. And using this formula, you can simply calculate the soil carbon stock in your soil. And it is very easy, and only carbon content you can measure from the soil laboratory, and depth you are knowing, because if you are collecting 0 to 25 centimeter depth, so it is 25 centimeter. Okay, and bulk density also you can measure in the laboratory, or sometimes we take the standard value 1.3 or 1.35, and we can estimate the organic carbon stock. So I did soil carbon stock assessment of India, and in India we have taken around 1200 soil samples throughout the country, and based on the where to take the soil samples, this we have decided by considering the land use, topography and agroecological region. Means slope, land use and topography or physiography was taken into account, and then we decided where to take the soil samples, and based on the soil samples we prepared the soil carbon stock assessment of the country. And we found that in India, that is the soil carbon stock present is 22.7 petagram in soil organic carbon, and inorganic carbon is 12.8 petagram. In India it was taken up to 0 to 100 centimeter depth. And forest area we estimated that is in the forest soils we have 9.38 petagram of the carbon present in that one. So how much carbon stock is present, based on the 1200 samples we are able to generate the map for the entire country, and this is the sample where we have collected the soil samples. So this is the latest estimate of the country for carbon stock in the country. So details you can read in our paper also. So at the end I say that the remote sensing data is quite useful for generating the reliable information about soil and land resources, and as the information is very much required for efficient and effective management and planning of your natural resources. We go for the agricultural land use planning or forest land use planning or watershed management or urban planning. For every planning we need a good information of soil. How we can generate the information of soil using remote sensing data? In the very beginning I have demonstrated and I shown that is how you can generate. And this remote sensing and GIS becomes a very effective tool, not only generating the soil resources but mapping degraded lands, estimating soil carbon stock and assessing the soil quality for better planning or better nutrient management. That's all. And you see that is we need to know about our soils. If you are not knowing about the soils, then we are missing an important part of our natural resources. Thank you very much. Now I invite you